Okay, everybody, this is lecture number 1, and I don't see any brand new students here, so I'm going to assume you're familiar with how to get the lectures and where to download this from. If not, check me at the break, and I can fill you in. I just kind of want to minimize all of the routine stuff that I have to give you this morning. So what we're going to look at is actually, believe it or not, Chapter 1 of the Norwich book, which is an introduction to artificial intelligence. And so we're looking at, and this is why I said I'm going to save the course overview and I'm going to save the course information for this first lecture because it's kind of mixed in along with the definitions. So the overview of the course is pretty much a foundation of symbolic intelligence systems, agents, searching, problem solving, logic, some representation, some reasoning, symbolic programming, and a little bit about robotics, but I can't really get into too much robotics in a semester-length course. This is really a second semester of AI that would give you more robotics stuff, because then you're combining a lot of things. But I'm going to talk a little bit about robots and then kind of the artificial intelligent components that are associated with that this weekend. In terms of prerequisites, some programming, some discrete math, some statistics actually might help you, especially when I start looking at networks and searching and sorting and all those sort of different discrete mathematics concepts. Although it's not a math-based course, you're not required to know any of the algorithms or any of the programming theory that is associated with artificial intelligence. In fact, there's no prerequisite for knowledge of C or C++, although the book assumes that. So when you start reading it, it's a little heavy. It's a little heavy because he's assuming you're a computer science, hardcore computer science student, and he's going through algorithms and he's going through math calculations and statistics and all this stuff that you might not necessarily be familiar with. So the book is very high level, probably why the Stanford people like it, kind of reinforces certain concepts that are taught in other courses as well. Why study AI? Because everybody uses it. It's not a futuristic technology. Google uses it, Yahoo, search engines use it. In fact, I'll talk about search engines today. The concept is that they are what's called an intelligent agent in AI terminology because they're working on behalf of a human and they're performing intelligent behavior and intelligent analysis, and which makes it, fits into that category. Labor, you see this little robot over here, which is actually kind of interesting. It's like for fun. It's supposed to be a space robot. So the thing is humans, we're fragile. We catch on fire. So do robots, but we're more valuable. So for working with explosive materials, for testing bombs, for, testing cars. You have the little crash test dummy. He's an AI application, actually. You put him in there, you put sensors all over the body, you crash him against a brick wall. So instead of hurting a human, you hurt the dummy. But then the dummy can come back and survive. And the dummy can come back and say, I had 200 pounds of pressure on my forehead, and I had 500 pounds on my left arm and right arm. And they can kind of test where the airbag should go or something, given the average height of the dummy. Believe it or not, they have different sized dummies, which is why they can determine if you put a child below the 5 feet, I think it is, or is it 4 feet? I don't know. Don't quote me on this stuff. That there's a 90% likelihood that the child's going to go through the front windshield even while wearing a seatbelt, which is kind of interesting. So they can come up with all of this information, which is why you never put a child in the front seat, by the way. So, because anyway, well, unless it's a big child, because the force of the gravity will even put a baby carriage thing through the front windshield. And if it doesn't make it through the front windshield, there's a 90%, there's a slightly lower, like a 70 to 80% chance that it's going to be squashed from the dash. So anyway, long story short, the likelihood of survival is very slim. But it increases by 50% if you just move them back one level, put them in the back seat. But a crash test dummy, through an artificial intelligence simulation, was able to determine all of this information to set the rules for the humans. So what we have here is space exploration. We have a lot of stuff, in the past where people got blown up in spaceships, and now we don't put people in there anymore. So we have a certain percentage of people. We have a certain percentage of robotics. They can last longer without oxygen. They can basically do things that humans can't do. Over here we have, in terms of science, the government has a DARPA, I'm saying that wrong, DARPA projects that go out and build robots that do tanks. There's self-controlled tanks and equipment and things for military service. So the U.S. government is pretty heavy into robotics for combat, actually, and also for artificially intelligent systems to detect certain things out in the field, which is interesting. In terms of appliances and applications, everything is electronic these days, so everything has AI components, and they are considered AI components. So most people think, oh, it's just automation. Some of the automation is considered AI, and I'm going to go through a definition of AI in a few minutes, but usually after chapter 1, the reader is looking at this going, well, what's AI? You thought you knew what AI was, and then all of a sudden it's like, oh, now you're questioning, is that AI? Is that AI? Because artificial intelligence is really all around us, actually. So it depends on your definition of it. In medical field, we have artificial, well, actually we're getting artificially created organs that are bioelectronic. So you can replace an organ with a computer that's really acting like an organ that has the same capabilities, does a better job sometimes at certain things. So it really depends upon the application. Also manufacturing. A lot of manufacturing plants will actually use artificial intelligent robots and robotics because, a human wears out after so many times moving something back and forth. So you put a robot in there and, they can move 1,000 times and you just replace the robot when they break their arms, or the arms wear out. So here's a Honda humanoid robot, learned how to talk, learned how to turn, learned how to go upstairs. So I'm going to, basically these links still work, so if you click on the links you'll see the actual stuff. But it's just kind of examples of teaching a robot how to learn. Here's our Sony AIBO. Actually, one of our professors, actually Dr. Liz Lee, actually worked on this project over at Sony, which was kind of interesting. I didn't find out until she brought the dog in. I went, hey, that dog looks familiar. And she said, oh, she built some of the controller stuff for it, which was kind of fun. But this is dating back in the 1970s, 80s. This is kind of a while ago. We haven't really seen too much in toys that have really advanced. There are some new products on the market, but artificial intelligence has a place in the community, like way beyond play and toys. So there's been a lot of experimentation in the terms of natural language processing and natural language questions and learning systems, which is kind of the predecessor to a lot of the, ask me what you want, Siri. And Siri comes back and says, oh, here are the 5 locations, which is essentially reading what you're saying, analyzing what you're saying, and then providing a response for you. So, which is kind of interesting because this is one of the original ones, and it came, in fact, the movie AI actually kind of showed a little bit of the natural language processing from the beginning. This has been going on, however, for a very long time, so Siri is nothing new, really. She's just a more advanced version. So, I don't know if you guys have seen the YouTube video of Siri with the Big Bang Theory. Yeah. She takes Siri for a date. Yeah. That was so hilarious. Because it's like, treating Siri like a person, and in essence, she's acting like a person, which is kind of interesting and funny at the same time. So if you haven't seen it, it's on YouTube. Just Google it, and you'll find it. Big Bang Theory and Siri, actually, you'll see it. It's actually kind of hilarious. And basically what we're looking at is it's really referred to as natural language processing and natural language learning or questioning, which is what Siri is doing. And we had, Siri was nothing new. We had Ask Jeeves. We have from the old days. And anyone who remembers that irritating paperclip in Microsoft Office in, I think it was like 2003 version of it or so, introduced a little paperclip that moved around in the lower right-hand corner. And it says, ask me a question. You didn't do it verbally, but you typed it in. It says, how do I find this? And it comes back and it went over and it showed you how to do stuff. Well, that's kind of like a Siri predecessor, earlier version of the concept. We have robot teams, and here's a USC robot lab that looks at teams, and this is actually kind of like our AI lab. Actually, we have a lab like this over at ITU. It's way down the hallway on the first floor. They moved it. It used to be upstairs, but they needed more space, so they moved it downstairs, where they have a robot that's actually moving on its own that is self-navigational, so it doesn't take instructions. So it navigates throughout, well, it has a little course set up for it. But hopefully, eventually, it'll be navigating throughout the building on its own. Well, we actually have something sort of similar to that in terms of vacuum cleaners. Yeah. And the book actually talks about the self-propelling, self-logic of the vacuum cleaner that goes around. And we'll take a look at the logic that's programmed into the vacuum cleaner, which is part of the AI concepts that we're going to learn for this course. How to map out the solution to that and how to design that. Which is why I think this class is kind of fun, because it's not like dry computer science. It's kind of like making it into applications and using it for something. So what is AI? Well, here's the test that originally started out when people said, well, can you call it AI? Well, we have some definitions of AI. They're organized into 4 different categories. And if you look at the bottom of the screen, and hopefully that shows up, okay, good, it does show up for you. So systems that think like humans, and then systems that act like humans, or systems that think rationally, because humans actually don't think rationally, so is that really AI? They're not really thinking like humans, so it's a different category. Or systems that act rationally. Some humans don't act rationally either. So we have to go, well, that's artificial, but maybe not intelligent. So intelligence is supposed to be making right decisions in some definition. So these categories here are meant as a guideline. And this is the 4 categories that have come out of the research from the beginning of around the 50s, when artificial intelligence became its own, around the late 40s, early 50s, when it became its own subject matter. And that's actually around the 1950s is when languages like Lisp and Scheme and Prolog started being developed. And they were programming languages to develop solutions to solve AI problems and scenarios, which is what we're going to be looking at in this class. So exciting new efforts to make computers think machines with minds. This is right around the 85, full literal sense. They think like humans. So each one of these 4 are quotes that go in from each one of the 4 categories. So if I were to ask you on an exam, what are the 4 categories of that you can place AI into from a historical perspective, they would be these 4 different categories. They would be looking at systems that think like humans, act like humans, or they think rationally or act rationally. Because we have rational agents, and then we have search agents, and we have agents, and we have different types of agents, and I'm going to talk about agents in a few minutes, that mimic humans. So then that's just one kind of technology that's applied in artificial intelligence. So acting humanly. Well, the original test is called the Turing test. It wouldn't be an AI course if I didn't introduce the Turing test to you. So Alan Turing, back in 1950, wrote an article, and there's a link to to this particular article, and you're going to read this article in one of your in-class assignments that we're going to do today. So you'll know all about the Turing test by the time you're done with this. And the article is only a page or so long. It's not a huge article, not a lot of reading. But it's not a bad article to be familiar with. It was in Computing Machinery and Intelligence, and it discussed the conditions for considering a machine to be intelligent. So he was really the first guy who said, well, let's give it a test. And let's see if this machine is intelligent, because you're calling it intelligent, but we don't know if it is or not. So, can machines think? And can machines behave intelligently? Well, the Turing test was an imitation game. So, this is a big wall, and we have the human interrogator over here. So, we have a human who's going to test. So, you put up a big wall so you can't see what's behind the wall. And you have 2 things behind the wall. One thing's a human, the other thing's a computer. It's the intelligent machine. And the test is to see if the human can tell the difference between who's answering. And it's not who's answering in terms of it sounds like the human, It's the intelligence of the answer that's being received from both of the 2 sources. It's like the blind test, In fact, in the 1950s, the commercials were, here's the blind taste test. Here's Coke and here's Pepsi. Can you tell the difference? And they put a blindfold around the person, and then they tasted it. And then some people could tell the difference and some people couldn't. Is it butter or is it not butter? They had all these different tests that came out. But it originated from this Turing test, actually, and was can you tell the difference? If you couldn't tell the difference, then it met the AI component and it really felt like a human, and then it was artificial intelligence. And then if it failed the test, then it wasn't artificial intelligence, according to Alan Turing, according to this experiment. However, this has been disputed through time, and a lot of AI today would fail this test. So it's not what I would call a set-in-stone scientific proven method for testing if something is AI. And there's a lot of controversy. There's a lot of people who have written subsequent articles that have challenged the Turing test and have come up with other ideas. And so that's part of one of the assignments that you're going to be doing in classes. Kind of look at this thing, read the Turing test, and see what do you think about this. And then I'm going to ask you some questions about it in one of the assignments where you're going to have to, respond with your own opinion, kind of thing, because it is an opinion-based thing. So computers need to possess natural language processing in order for this to work. They have to possess natural language processing, knowledge representation, automated reasoning, and then machine learning. So those are the concepts that we're covering this weekend, actually, in terms of the definitions of them and how they fit into the AI realm. So are there any problems or limitations to the Turing test? Tons of them, actually, because not everything does natural language processing. Siri does natural language processing. If we could put Siri, which is why that Big Bang Theory YouTube video is actually kind of funny, because she answers just like a human. So if you put her behind a blank wall, and then in reality, towards the end of the video, she is a human. You see her in a human form, so you know she's real. She is confusing because you don't know if it's a real person or if it's a fake person. It would pass the Turing test, but only because it's using natural language processing. So your search engine, if you said, typed in, find me digital camera information, it comes back and gives you all the digital camera information, it would fail the Turing test because it's not giving you back in a human-compatible, human-simulated thinking process or natural language processing. It's using text, and it's giving you text, and it's giving you visual clues, but it's still artificial intelligence. That's a search agent. So it still falls in the category of artificial intelligence, but it would fail the Turing test because it's not working with natural language processing. But you have to imagine in the 1950s, we didn't have computers. we didn't have audio, text to audio or audio to text. We didn't have audio processing. We didn't have natural language processing. So you have to kind of take the age frame in which this was done and sort of, which is one of the problems with the Turing test today. It's outdated in terms of the technology that was available back then. So the definition is slightly off. So what tasks require AI? So AI is the science of engineering, making intelligent machines, performing tasks that require AI intelligence when performed by humans. What tasks require AI? Almost every task. And here's some examples here. Solving a differential equation. Brain surgery could require some AI. Inventing stuff, playing Jeopardy could require AI. Playing Wheel of Fortune. What about walking, grabbing stuff? They may require AI, depending upon how you're simulating it, what you're doing. So basic, any concept in the world, any task in the world, could be an AI solution, could have an AI solution to it, depending upon the problem set and the task that you're working with. So it's kind of, people who don't like abstraction hate this concept because it's like, well, no, you're not giving me a clear understanding, you're not giving me a clear definition of what AI is. Well, that's the interesting part about artificial intelligence. There isn't any. It's whether it is or it isn't is up to the person judging it. So this is the same thing that we saw before in the last slide, but on the bottom we have a new piece of information. It says problem number 1 here. The Turing test is not reproducible, constructible, and amenable to mathematical analysis. How can you take, well, actually, believe it or not, that machine would probably have more accurate results than the human these days, given, average intelligence levels and math capabilities. We don't know about that. What about physical interactions with the interrogator and the environment of the interrogator, which is not taken into consideration? And also, the total Turing test requires physical interaction and needs perception and actuation. Well, it needs feedback. So one of the other problems with the Turing test is the form of the feedback. As I was mentioning before, when you run the intelligent agents of Google or Yahoo, we're getting different feedback, or it's not coming back in a human form. So it's not a human, so it's not artificial intelligence. So it fails the Turing test. So, believe it or not, nobody else has come up with a test like the Turing test that would actually be equivalent or would be as accurate. Because I think people are afraid to, because how can you? AI goes over many different fields, and here's an example here. What would a computer need to pass the Turing test? Well, they're going to need to have these particular AI components. but this is just a subset of all of the AI that's available today. So what are our subsets? Okay, so this is your vocabulary for today, or for this weekend actually, because these are all the concepts we're going to be going over. Starting with, well, I'm going to hit natural language processing in the first couple of lectures. Communicating with an examiner. So natural language processing is anything having to do with communication. So the spoken word, the written word, the non-written, non-verbal communication is also natural language because it's a language for communication. So any of your OCR applications that take and create from a scanned image, convert it to text, convert it to audio. So technically all of the read me my email messages kind of things, text interpreters, they're slightly artificially intelligent depending upon how much changing they're doing and how much interpretation and how much correction. A simple translation from audio to text or text to audio is not artificially intelligent. It's not if it doesn't, it might be artificial, which it is, but it doesn't apply intelligence for the definition. So there's a distinction that's common these days that says, is it a computer program or is it an intelligent computer program or algorithm? And they're judging it on the intelligence. How intelligent is it? Because there's tasks that we used to think were intelligent that aren't intelligent anymore. As an example, a calculator. Actually, a computer is not intelligent anymore. It's an appliance right now. So it used to be artificially intelligent. It used to be not anymore. So as we go through time, the intelligence is the key. If it's a mundane task that anyone can do, not intelligent. So a robot that can walk, great. It walks. It's not intelligent. A robot that can think where it's walking to and follow commands, intelligent. So again, yet another way of deciding whether something is artificially intelligent or not. So natural language processing has to deal with communication and mimicking intelligently what we're calling human communication. It doesn't actually have to be human. We have artificially intelligent applications that train dogs. In fact, there's a couple of security systems that, in California they have these actually. People don't like to put fences up. They like to leave their yards open. But they can create an intelligent system where the dog only hears it. If they get close to something, the dog will hear a noise, and then they'll move away. So it's kind of a sensor system that's artificially intelligent that communicates with the dog through sound, that tells the dog where the dog needs to go throughout the yard and where they can go and where they can't go. It's kind of like negative reinforcement. It's kind of like those collars you put on them and they go zzz. If they go somewhere they're not supposed to go, they go zzz. Well, it's actually a training technique. And so the dog's not going to want to get a bolt of electricity through their neck. So they're not going to go there once they've learned that. And it's a learning system, which falls under the machine learning category. So the collar, this is number 1, 2, 3, 4 on my list here, adapting new circumstances to detect and accelerate patterns. So that artificially intelligent collar, which is a training technique, emphasizes machine learning, but the machine is the human. So it loosely falls into the category. We also have programs that learn on their own. These would be genetic algorithms. These would be neural networks and things where we put the information in through a network. And then we learn the patterns. And then once we've learned the patterns, then we can alter and the algorithm itself can change. That's artificial intelligence. It falls under the concept of machine learning. The algorithm can change and adapt towards the environment. As an example, credit scores. If our credit reporting system bureaus, in the US we have 3 of them, they use 3 different algorithms. They're actually expert systems. They take all the data about all the cards you've had and all the houses and cars and everything you bought essentially, and it gives you a score. Somewhere between, I think it's like around 700 or so is good or something, I don't know. I'm not going to tell you what mine is, but we're labeled on our score, and our score tells us how much we have to pay in interest rates and how much we can borrow and what we can do in life, right? It's all based upon a score. Well, back about a couple of years ago, we had the housing crash in the market. If you take all that stuff as a flat algorithm without using any AI and just take all that stuff, as you go through times, you have periods in which the economy goes up and down, people lose jobs, people lose houses, I don't know, your stock market portfolio went down to the tubes, you don't own as much as you used to own. So, and it's temporary until the stock market goes back up. Well, the artificially intelligent component of the credit reporting systems takes that into consideration. Otherwise, everyone would end up with a bad score, and then it would defeat the purpose. So it takes economic conditions, it takes pricing, inflation, all sorts of different environmental factors into consideration, so your score doesn't fluctuate when the economy goes bad. Your score stays the same. So your score doesn't go down when your assets go down because your stock portfolio went down because the economy's bad, because we're hitting an election right now, blah, 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 blah. So anyway, so that's machine learning in terms of a category. Also machines that learn about environmental space, if it's a robot or something like that. Okay, so going back up here, knowledge representation. So we have to take human knowledge and put it in a computer, or put it in a program, or represent it somehow as data. So anytime you take and you store and retrieve information that's being provided, that's provided before, during the interrogation, or that's used in the AI application, that's knowledge representation. Which means you build a database. So Prolog is an example which does logic processing, builds a database of knowledge. And we have a knowledge engine, or a knowledge base as they call it, which falls in the category of knowledge representation. So automated reasoning. Well, using our stored information to answer questions. Well, that's another thing that Prolog does for us as well. It takes the knowledge and it answers questions. An example of this would be the weather reporting systems. So everyone checks the weather. Actually, I checked the weather this morning because I was going to ride my Vespa, and I was going to do it, but I was running late, so then I ended up taking my car. But today's the last day I'm probably going to be able to be outside, because tomorrow it's partly cloudy. By the end of the weekend, it should be raining. Believe me, yeah, we're going to have rain, actually. If you check the weather, and you say, how did they know that? How did they know that? Well, it's an artificially intelligent weather prediction system. It takes all of these factors in, represents everything as knowledge. And what's knowledge? Well, cloud coverage, precipitation, I don't know what they're measuring, but all this stuff comes in, and then they can say 20%, 30%, 40%. So next week it's going to be pouring down rain. By next Wednesday, it's a 70% chance of rain. And it's increasing as we get towards the middle of next week. But it's a beautiful day out. If you were to ask me today, if I didn't look at this information, I'd say, hey, it's gorgeous, California day. But this is our last weekend, by the way. So let's see if I'm right. But it's not me who's saying this, it's the data that I'm looking at in terms of the knowledge representation that's given to me, that's answering a question for me. It's doing some automated reasoning and it's saying, bring an umbrella, it's going to rain. So I'm like, oh, well, it doesn't look like rain today. But artificial intelligence is telling us, in fact, most of those weather systems would be considered artificially intelligent because they're taking all this stuff and they're thinking like a human. And if you put all the different combinations together, then you're going to have rain. So it's going to tell us that. So stock market programs, there's a million of them out there. Only problem is people that buy those stock market programs, they say buy this, sell that. Their stock analysis has been done for years. Everyone buys it. Everyone does the same thing. It blows the concept. So if we all know it's going to rain, it doesn't really blow the concept. It just means we dress appropriately. If we buy the stock program and we start looking, then everyone's going to mess up the phenomena. So then there's programs that deal with the popularity of the stock programs that tell you if so many people own this program and are using it and are making their decisions by this program, then there's another program that tells you what the effect is going to be with that. If those people behave like they're supposed to do, then this other program is going to tell you what to do and to counteract all that stuff. And then there's another program that tells you what to do after that one's done. So it's interesting how the knowledge and the manipulation occurs. Vision, another area of artificial intelligence. So for the Turing test, we have vision to recognize the examiner's actions and the various objects represented by the examiner. So vision is taking, if we're a robot, the scene in which we're looking at into consideration and identifying objects in the scene, and then being able to basically perform calculations on the objects to see what we're going to hit, what we're not going to hit. And I have an example of that coming up, so I'll save that one. Motor control, which is also part of the total test, to act upon objects as requested. So motor control refers to, I asked Siri a question. Did Siri answer? There's her motor control. And how did she answer? Yes, I found such and such, which is natural language processing with motor control. So you're you're responding to stimuli. So sit, the dog sits, that's motor control. Show up at 9 o'clock a.m. Some of you guys had good motor control. Other senses, such as smell, touch, audio, audio senses can also be mimicked artificially. So, and then you're sitting here going, well, what's going to be on the midterm? All this stuff. So, this is stuff that's defined in the book as well. So this is your basic terminology in terms of, when would these pass? Some of them would pass and some of them would not pass the Turing test, by the way. So in terms of thinking humanly, cognitive science gives us how we think. Gives us, so here's where artificial intelligence overlaps with psychology. So a lot of psychologists are playing a huge role in the whole psychological state of the human. So there's positive reinforcement, there's cognitive science, there's all such many behavioral sciences come in here with learning theory, behavioral adaptations, and saying, well, if you treat a human a certain way, they're going to respond a certain way. So if you can treat a computer the same way as you treat a human and it responds the same way, then it's thinking humanly through its senses, through its cognitive behavior. So cognitive recognition, information processing, and psychology replaced behaviorism around the 1960s or so. So it brings together the theories of experimental evidence, solves activities of the brain. So what level of abstraction? Well, we have knowledge or circuits or connections. So a lot of neural networks are actually trying to do this, build connections. So a lot of the natural language processing, the way that actually it's built in with Siri too. But you see this usually with the primitive text programs. There's a couple of programs out there where you can have friends. And sometimes this makes you wonder, actually, when you go online and you meet friends that you don't know. Well, how do you know that they're not a part of the Turing test? And they're not artificial intelligent people. You say, hey, how's it going? It responds back, hey, good, And it acts like a human, responds back. Well, it's responding to stimuli. So if you use certain words, it goes, oh, you're upset. So it might come back and say, hey, what's wrong with you today? Because you said, damn, I missed my class this morning. I showed up 15 minutes late, and she wouldn't let me take attendance. And then the computer comes back and says, sorry, man. Better luck next time. It comes back, and then it feeds the human emotions, which, you think about it, are we just all robots? Because we're so predictable, which is kind of interesting. So the cognitive science gets into, well, let's understand how the human thinks. Let's understand, what the behaviors are. And believe it or not, they're pretty good. They come out with this whole template of human responses. And you can actually come out, and there's a couple programs out there that do a really good job of actually, and feeding the ego, and feeding, in fact, Siri sort of does that too. Say, hey, who's the best person? You are, because, you want to be like, and cognitive science actually works with UI design as well. So if you take a human-computer interface program class, you learn about UI. For number one thing, make the user feel happy. The user always has to feel happy, and you have to use color combinations that promote happiness, and you have to use reactions and stimuli to mouse clicks that promote happiness. And it's all about making the human feel good about themselves, which is kind of weird. But it actually works. No one likes a program that they don't like, that doesn't like them. So, and it's a computer, not a human. So how to validate models, predicting and testing behavior of humans from top down, directing identification from neurological data, bottom up, building computer machine stimuli models, and producing results or stimulus that comes along with it. And if you think about the concept of neural networks, I can describe to you, and you can stare at this slide as I describe it to you. I can describe neural processing for you in about 2 or 3 minutes here. It's about knowledge representation and the connection between the knowledge. And we can take, and people think, oh, neural networks, it sounds like it's so sophisticated. You can actually draw your own out on a piece of paper in about 10 minutes time and actually do a really good job with it. Take all the connections of all of the information you possibly learned. Now that you're sitting here as an adult, you didn't start out this way. You got here somehow, and you got here through neural connections, because when you were a baby and you were born, you learned how to breathe, and then you learned how to walk, how to talk, and you went through different stages and you went to school. But it's connections with data. So if anything, you're just a big hard drive with a neural network. And the neural network is the synapses or the connections that you make, which gives you deja vu, which gives you, oh, I remember that. And you recall and you connect pieces together. As an example, the first time you learned what hot was and what cold was. You learned what hot was by experiencing it, making the connection, so you burned your finger. Everybody in here either burned their finger or froze their finger. Or their hands or some part of your body. Some skin got in contact with something that was extremely hot, and you learned what hot was. And then you tried it, depending upon how intelligent you are, you saved it the first time, you stored it, or you didn't save it, you ignored it, and you did it 5 more times, and then eventually you're going to get it. So students, when they start learning subject matter, they go, I can't learn this. It just means you can't learn it on the first time. You just have to do it 5 more times or 6 more times. You're eventually going to learn it, but you have to figure out how to save it. Once you figure out how to save it, then it's there, and then you add more to it, so your hard drive gets filled up. And then when it eventually happens, you go, oh, hot. I know what hot is because I put my finger on the stove and I burned it. Actually, I don't think I did that, but anyway. And then you see a candle, and you feel the heat, and your senses work with the heat, and you go, oh, and you have the sensation, hot. And it comes back and says, oh, I know what hot is. And you go, candle's hot. And then you learn what's hot, and you learn what's cold. It seems kind of primitive, but that's actually part of the cognitive learning process through senses. Actually, it's not cognitive. It's another branch of learning theory, but it goes through sensory reception and connections that we're making through neural networks. So when you're thinking about stuff, the first thing you do is recall. So you go to your hard drive, which is your brain, and you go, what do I remember? What do I remember? And then you use that as a reactive mechanism along with your senses. So you're sitting in the car, and you're driving a vehicle, and a ball gets thrown out into the middle of the street. And some people go, well, ball, child, probably following the ball. So your immediate reaction is an impulse, and the impulse sets a reflex, and the reflex says, slam on the brakes. So if we know that, then we, as humans, can make artificially intelligent brakes that know what a human's going to do, and then create anti-locking brakes. Because the human is going to step on that as hard as they can, as fast as they can. And that's how anti-locking brakes came around, because we have an artificially intelligent braking mechanism that works with the reaction of a human who doesn't know how to press on the brakes properly because they're not responding. They're responding out of their neural network and their senses, and they're not thinking intelligently. So the car is thinking more intelligently than the human in that particular case. So anyway, long story short, this is how some of the artificially intelligent human behavioral programs and research has evolved in so many different fashions and different ways. So thinking rationally is another component. So this was thinking humanly. To think humanly, we're using our senses, and we're not necessarily thinking rationally when we think humanly. We're using stimuli, we're using connections and synopsis that we've made between different data and different collections. To think rationally, that means we always make the right answer. Do humans think rationally? No. We would think rationally if we didn't have senses. If we didn't have feelings, if we didn't have a sense of taste or touch or anything. Actually, if we didn't have taste, we could not taste a thing at all, which is a sense. We would be eating better foods. Certainly foods that didn't have salt in them. Certainly foods, because salt enhances the taste buds. It's for humans to taste more. So we would be probably healthier beings if we didn't have that. So rationally, when you go to lunch today and you make your lunch selection, you're not thinking rationally. Most of you are not thinking that, unless you're odd and you're on a health nut who only eats certain foods. Like you only eat, so there's people out there, go through these diet things. They only eat fruits and vegetables and stuff because they're thinking rationally. Normally people don't think that rationally. They eat whatever tastes good from their senses. So that's what rational thinking is. So when you go to lunch, you're not thinking rationally. Otherwise, you would have the salad instead of the burger or whatever it is you're going to eat for lunch today. So Aristotle here attempted to codify the right thinking. And what are the correct arguments and thought processes associated with that? Socrates says, A man are mortal, therefore Socrates is mortal in terms of the example. So since Greek schools developed various forms of logic, the notion plus rules of derivation for thoughts occur. So one of the problem might be uncertainty. Not all facts are certain. The flight might be delayed. Something might happen. So we can't always think rationally because the plan always changes and we have to modify that rational thinking. And then we also have resource limitations. There's a difference between solving a problem in principle and then solving it in practice. Under the various different resource limitations such as time, computation, accuracy. Good example of that is purchasing a car. People actually make so many mistakes in the rationality. And because we don't necessarily have all the information, we don't have all the resources. But the internet actually helped us with that because now we have more resources. So it's the assimilation of information. The more information we have, the more rational we can be because the more correct we can be in our answer. So we can justify why we purchased something versus, and that's why they call it an impulse buy versus a researched decision. So a lot of people go through life impulse buying everything, which is not bad. It's just that you're not thinking rationally, but you always have to think rationally, which is another question. So that's kind of where AI kind of goes into the philosophical kind of realm versus the psychology. So philosophically, are humans really rational? And so do we expect computer programs to be rational? So Siri, if you say, Siri, will you marry me? Siri will come back and say, well, I'm not the marrying type. I think it actually says that, but ask it irrational questions, and it comes back with irrational responses for you because it's working with rationality. So you can ask it anything, and it will always come back with a response. The responses are irrational for human thinking. So if it doesn't want to say yes or no, I'm not really the marrying type, which is really no, but it's passive aggressiveness. So, or not passive aggressiveness, but it's something else in terms of the irrational response of humans. So it's kind of like you say, well, do you want to show up today? And I'm, sure, why not? But is sure, why not? Is that yes? No, that's not yes, because we're not rational. We're irrational. You're going to say, well, I know I'm supposed to say yes, but I don't want to say yes because I have something else I want to do. So, sure, why not? And it's more like, okay, but, what are you really saying? So try to put that in a computer program. That's a challenge. If you could put that would pass the Turing test, actually, if we thought rationally. But, I don't know, or irrationally, make it think irrationally. So acting rationally, another thing. So the reactional behavior says you're doing the right thing. Or whether you're doing the right thing right, or you're doing the right thing. So you get this in robotic behavior all the time. When it walks into a wall 10 times, is it really acting rationally? No. Rational behavior was after you hit the wall once, you back away, and then you go into a different direction, which is what a human would do. So that's kind of the test in terms of the rational behavior. Providing the most general view of AI because it corrects interference, laws of thought, uncertainty handling, resource limitations considerations. If you combine humans' lack of thinking rationally with their lack of acting rationally, then you get criminals. A moment of opportunity, when you don't act rationally. When, oh look, someone dropped a $100 bill. And then the act of picking it up and putting it in your pocket, not so rational in terms of human behavior. And then later you think, why did I do that? And then you think about it, and then your human reasoning comes into place, and you go, okay, so I wasn't acting rationally, and I wasn't thinking rationally at the same time. Because the person saw me do it, now I'm going to get in trouble. Because you have that fear of rules. So in terms of a society, we build rules, laws, that make us act rationally, theoretically. And if we don't act rationally, we get in trouble. So, because we get in jail, usually, for stealing or for doing stuff. So that tells you humans aren't perfect. So why do computer programs need to be perfect as well? But people think computer programs need to be perfect. But the thing is, artificially intelligent humans are kind of broken artificially intelligent programs too, because humans aren't broken. Or humans anyway. So this isn't Sunday, so I won't get into philosophy, but we'll save that for the end of the weekend. All right. So how to achieve AI? How is AI research done? It's actually crossbred. It's through research from both theoretical and experimental. There's a lot of data that's collected. Experimental science has both basics and applied aspects to it. So there's a lot of data collection, and then there's a lot of programs that are created to analyze the data, which is why we're going to look at prologue and scheme throughout this course, because that's used to work with the experimental results to come up with the artificial intelligence solutions. There's two main lines of research. One is biological these days, looking at biological human data, and the other one is phenomenal based. So on the biological one, it's based on the ideas that since humans are intelligent, AI should study humans and initiate the psychology and the philosophy of humans. That's the traditional approach. Now we're looking more along the phenomenal experience, where it's based on the study of formalizing common sense facts in the world and making the problems that the world presents to achieve, looking at those problems and achieving goals through, what the phenomenal actually is in terms of the human experience. So the two approaches interact to some extent, both eventually succeed. So it's a race for both of them. Both racers seem to be walking. They're not running. Essentially, it's kind of a slow progress, actually. So here's some branches of AI, and this is a summary from the chapter 1 of the book, Logical AI, Search, Natural Engines. And I've gone through most of these already. We have this concept of planning, generates a strategy for achieving a goal. That's going to be the focus of the next lecture, actually, so I'm going to save that. But we can plan solutions to AI problems, and the planning process is part of the study of AI. How do you come from a proposal to a solution, and how do you map out the problem scenario? It's not like programming applications. It's a little bit different than that. In terms of the prehistory of AI, we're looking at, these are just the different fields for which we have this cross-section, because as remember before I said AI is a sort of a hybrid study. So we're looking at philosophy, mathematics, psychology, linguistics, neurosciences, essentially. And you can go through the history. Looks like I was a little late. I said around the late 40s, early 50s, or this is around the early 40s. I'd say we have the first kind of mimicking of humans that's going on in science. So it hasn't really been around for that long as a field. So we have this. We have AI tests that go on still. In fact, we have we have prizes for AI inventions and stuff. And one of your scientists is going to have you identify some of that stuff. Look at that. The AI state of the art. Have the following been achieved by AI? World-class chess playing? Kind of, sort of, actually. Computers that beat humans now. Sort of, kind of. It's like they still have a human that beats, at least every year we have one human that beats computers. Playing table tennis, cross-country driving. Yeah, we do have that. The Google car that's out there, or the automated cars, actually, that drive themselves. And I'm sure you guys have heard of that on the news recently. So they're getting ready. In fact, the interesting thing part about that is, what happens with the DMV? Do people need licenses anymore when the car drives itself? So I'm thinking maybe in another 20 years from now, hopefully I'll be alive for it. We get into the car, we press a button, and we say, where do you want to go? We type it in, and the car just takes us there. So humans don't have to drive cars. You know how many accidents that would solve? There would be no more automobile accidents if you thought about it, because these humans, they don't think rationally. But you always have humans in the equation, because the kid with the ball is still going to occur whether a human's driving the car or whether a machine's driving the car. But the machine might be able to react a little bit better to it. Who knows? So if we can improve that, we can actually improve the number of accidents and decrease it. But then do humans need driver's licenses anymore? Well, that's going to be an interesting question. So maybe the driver's license 20 years from now, actually, when we're like we're going to be like older. Remember remember when we used to have a driver's license? Oh, I don't have those anymore. All right, so this is the rest of this lecture I'm going to kind of skip through because you can read it on your own when you get bored. It's just going to give you the map for the course and the map for the textbook. Chapter 1 is what I just covered right now, actually, the history and kind of an overview of what AI is. The next lecture I'm going to get into is in the Intelligent Agents, which is Chapter 2 of the book, so you want to read that chapter. Chapter number 3 is going to get through problem solving and searching. I'm going to get through that this weekend as well. And then I'm also going to cover uninformed and informed searches as well. And then we're going to have a break, and you're going to come back for the next weekend, and then we're going to do the gaming. So I'm kind of trying to mix it up a little bit. Gaming is going to happen, game theory and gaming is going to happen in the next weekend, Friday of the next weekend that we meet. And that's around chapter 8 or 9-ish. And then we have problem solving, which is really agents and reasoning. I'm going to actually get into chapter 10. I'm going to cover agents and reasoning logically today, actually, in the next lecture. I'm going to combine it with lecture 2, actually. And so chapters 10 and 11, so I'm kind of mixing around the book a little bit. This is a Wampus World game that's portrayed in the book. Actually, it's a nice little agent simulation that kind of shows you the reasoning process. And then we will also cover next time first order logic, which is going to be prologue, actually. And your assignments are going to deal with prologue. Some of the assignments that you'll be doing between now and next weekend. And building knowledge bases, which leads us into the concept of expert systems and knowledge representation. Expert systems, almost every information system used in a business environment today is an expert system. So we have the concept of scheduling a flight. You went through and used an expert system because you went through a computer-aided program that told you what seat was available, and it integrated with other programs, and the price of that seat was based upon the demand and how many seats are available on the plane. And the scheduling of that flight went through an expert system that scheduled it somehow, lined everything up. In the old days, people used to do this manually. Not such a good thing because it takes too much time. And what if there's a delay? How do you delay? How do you postpone all of the other flights? Or how do you change the routes or do something? Well, it's all done by computers now. And that's part of what's called a knowledge base, or a computer representation of knowledge, through expert systems. Prologue gives us our inference and our first order logic programming and logic reasoning systems. And then we'll look at, towards the end, next time we'll also look at fuzzy logic. And this is where we get air temperature controllers, our refrigerator controllers essentially, that are not going to work. Turn something on, turn something off, turn something on. It's not an on-off, it's a fuzzy, where, if it's within a particular range, turn the blower on. If it's within a particular range, heat up the coils to a certain level or something. So I think it's when birds fly over and we get the darkness. It just kind of makes us feel like we're outside, actually. I like this room. It's growing on me. All right, so we have planning systems. I'll talk about planning actually this weekend. So in fact, the next lecture I'm going to get into some planning concepts as well. So you'll figure out what you're supposed to do with that. Expert systems towards the end of the book. So like I said, we're not going to cover the whole book, but these are the concepts that we're going to cover in terms of expert systems, knowledge recovery. I'm not going to hit the sections at the end, but if you're interested in reading it, towards intelligent machines and kind of the supplemental stuff in the newer version of the book, the authors added some more robotic information in there as well. So I'm going to give you an example to kind of conclude with chapter 1 of the book. That's going to go into a driving example. And this kind of puts the pieces together and talks about environments, goals, purpose, and some of the things I'm going to be bringing up in the next lecture. So the goal of this particular project, and this is a driving example for Beobots, is kind of an old project that was done at the University of California. So the goal here was to build robots that can operate in an unconstrained environment that can solve a wide variety of tasks. So we have all the pieces and the components, and this is where computer science comes into place. So we can create a Beobot by a Beowulf plus a robot. Well, okay, so we can take and combine, rubber tires and engines and pulleys and things and build it. That's not really the artificially intelligent part. That's the mechanical part of it. It's building the robot itself. In fact, you can buy kits out there now. And kits, you snap together and you create a robot. But here's the example that I want to give you. We have a goal. And we always have to identify the goal in the problem solving. And then we have the purpose, and then we also have the environment, and then we have the route or the map to get there, which is going to be the controlling engine. And I'm going to go all through all of this in the next lecture. But this is just an example of it to see where we're heading. So the goal was to build one that can operate in unconstrained environments and solve a wide variety of tasks. So we have lots of CPU power, we have prototype let's say robotic platform. We have visual systems, cameras, that we're going to use to find interesting objects in the world and recognize, identify these objects. And then we're going to have different types of sensories for the objects, you know, if they hit something, if they see something. And what do we need to do? Build an external representation of the world, understand what the user wants, and then act upon those requests to solve the user's problems. So this is sort of like the problem definition stage of the solution. So the basic components of vision. So if I were to take this problem scenario and say, well, what is it that we're analyzing from an AI perspective? Well, we're looking at vision. We're going to look at knowledge representation. We also have sensory, which leads us into the vision. We're also going to have an environment map, and then we're going to have a controller. So I can kind of break it out into pieces that I'm going to use to solve this particular problem. Looking at the vision, we're going to have cameras. So we have a segmented, downscaled, original. So we have to figure out, well, from the scene layout, how much information do we want to capture? And from a real-time perspective, we have to go, well, and the funny thing is when you go into artificial intelligence and you start looking at this stuff, nobody's an expert in vision. Nobody's an expert in camera capturing. This is where your computer science background comes into place. So if you're familiar with graphics and vision, you know, if you take a camera feed, well, actually you can use a Go camera these days, but if you take a normal camera feed, the processing is too slow to do it in real time for a reactive mechanism, because you have to analyze the image that's coming in and clip certain pieces out of it to identify objects. So here we have a localization for a localized object recognition system that we're going to build. So we have one component that's going to take and identify objects that are going to come from a camera feed. And then we're going to position the camera. Here's like two cameras in the front of this little robot guy here. So it does show up, that's good. And then we're going to put the pieces together, and you can kind of see it sort of looks like our robot a little bit, the one that we have in the AI lab over here. And we have it all connected together. And then now what we're going to do is the main challenge is to extract the minimal sub-scene, the minimal pieces that we need, or the small number of objects and actions. Here's the given big scene, and we're going to represent the behavior from the noisy attention span paths, okay? Well, regardless of the terminology, what we're going to do is take the behavior here, analyze it in a way that we can represent it. So this is the knowledge representation part of it. So we achieve the representation for it that is robust and stable against the noise and the world motion and everything else associated with it. We do that by taking the input frame, and here's an example of it. Here's a track with a person running on the input frame. We have the track outlined as this portion here. We take and we look at the objects, and we have a man over here. I didn't even notice the tree or the cone, but there's a cone right here, if you can see that. So it's hard to see it probably on that projected image. If you download the slide set, you can actually see it a little bit clearer. But we take and we define the objects, and then we can route the robot's movement to take into consideration priority of the objects. So if we have a choice, we're probably going to hit the cone. Probably not going to hit the key, the tree, or the man. But we can see which ones are going to be important, so we can strip down the version and come into a general simplified format. So driving around the USC Olympic track, avoiding obstacles. So we take the data in, we do some memory and some decisions, we save the information, we do some plotting to position, to scale down the data and make it more readable. And then we can navigate around. So major issues that are with this problem solution is, how do you represent the knowledge about the world? How do you represent the objects that are in here? And if I were doing this personally, I'd put priority on it, but you may not be able to, because that's kind of a, your presetting priority stimulus. How to react to new perception events, things that are coming in. How to investigate new things from past experience. How to understand the user. How do we know that this robot that's driving this car doesn't want to hit everything. Maybe it's a bowling ball and it wants to hit all the pins or something. And then optimizing the balance between the goals and the environment, and then reasoning about what is the best course of action, and then the communication back to the user. So how to plan ahead and how to learn from experiences. Well, here's where the general architecture comes into place. So your general, what I'm giving you is an overview of a general AI solution. So you'd have your hardware components, you have your thinking, you have your knowledge representation, whether it comes through vision or other data sources, and then you have your general architecture. And your general architecture sometimes turns into your planning or your map. And your map, in this particular case, you have a task list, and the task list, and I'm not going to go through the whole thing, but it's associated with sort of a flow chart. It sort of looks like a flow chart because we're going through and you can see particular events. Up here you can't see it, but there's a but it says input video. Input video is going into a low-level vision, going into a surveillance map, and then the map, there's a controller here that's going to say, well, what happens if the map has this in it, if the map has that in it, and you have a basic flow chart of yes and no kind of decision making that's done to derive at a course of action. So every AI solution generally has some sort of a map in terms of its logic. Here's an ontology, which is basically a map for football, basketball, professional sports, non-professional sports behaviors. So think of it sort of like a flow chart, if you want to, or a connections map. It's a basic map that's associated with an AI solution for figuring out who's going to win, essentially, who's going to win a team sport of some nature. Here's a task relevant map as another example, where we have a user agent out here and scalar topology here that higher values for more relevant locations that might be associated with it. So here is the kind of the map of an input video coming into some vision recognition. This is the visual brain that goes to the agent, and then there's a task specific to it. So we have a long-term memory or kind of a storage of everything, a working memory. If you think about it, this is sort of like how the human thinks. You know? The map is supposed to be mimicking the human process in terms of the reasoning. So if I were an intelligent agent and I were working at Google and I was answering your request to find video cameras, I've got the information you gave me. I have the information other people gave me in the past, so I can kind of interpret to know what you're looking for. I can go out to certain servers that I know have higher priority because it does work on a priority system, by the way. It has certain information that's associated with things that I'm looking for. If I already know that, I can map out the solution. I can come back and then I can organize things, and then I can deliver it to you. Well, am I just not an algorithm then? So the question is, how do you take that algorithm and make it more intelligent, which is kind of the challenge in a lot of these problem solutions. So it's interesting how the solutions are created, and they're all unique. So more importantly, how are we going to do it from a programming perspective? Well, we're going to use objects and relationships, and we're going to figure out, is something close to something? And this is where Prolog comes into place. And this is the logic that Prolog can give us in terms of the analysis, which is why we're going to look at Prolog throughout this course. So this is the end of the first lecture, and we're going to take a 5-minute break, actually. So what we've looked at is Chapter 1. Actually, that was everything that was in Chapter 1 of the book. So it seems like not that much information, but there's a lot more detail in the chapter. So, which is basically giving us the outline for the entire book. So it's exciting. Well, it's a very exciting, actually, field. In fact, AI is more prominent right now than it has ever been. So it's definitely a growing field. And you can find a ton of different examples online in terms of AI. So let's take our first break. Let me stop the video first.